While the argument for an intelligent designer from biology may have its flaws, physics provides a truly compelling argument for an intelligent designer.
In this episode, we'll show that the qualitative laws of physics exhibit clear signs of being designed.
We'll move on from fine-tuning that focuses on the precise quantities in the laws of nature, such as how big an electron is, and turn to the design of the qualitative laws of nature themselves, like the law of gravity that all masses attract. This will lead to an independent argument for the existence of an intelligent cause of our universe.
Though it'll be a new and independent argument, its structure will be similar to the fine-tuning argument. We've already done a lot of the heavy lifting for the fine-tuning argument, which will make things much easier. I'm Rabbi Aaron Zimmer.
And I'm Rabbi Dr. Eli Feder. Welcome to Physics to God. Welcome. This is Physics to God, a guided journey through modern physics to discover God. My name is Eli Feder, and I'm an Orthodox rabbi and a mathematician.
And my name is Aaron Zimmer. I'm also an Orthodox rabbi with a deep interest in physics and philosophy. On this podcast, we'll discuss some of the most fascinating developments in physics and make a convincing argument that they point directly to the existence of God. When discussing physicists' search for a theory of everything in episode 1, we left out an element of what they're looking for in a final theory. Though this element wasn't relevant to the fine-tuning argument, it's relevant now. Physicists aren't merely seeking a theory that explains everything. They're aspiring to discover a unique theory that explains everything. By unique, physicists mean that it would be inconceivable for the theory to be any different than it actually is.
A unique theory of everything would answer the critical question that lies at the heart of this episode. Why is our universe governed by these qualitative laws of nature and not different laws? Again, this is a question about the qualitative laws, like gravity being an attractive force, not about the quantities, like the strength of gravitational attraction. As physicist Lee Smolin says in his book Time Reborn, we should be able to say why the laws of nature we have discovered, rather than others, are the laws. Facts about the world need to be explained, and a fact most in need of explanation is why particular laws are observed to hold in our universe.
For a period of time, scientists hoped that they would answer this question by discovering a unique final theory. For if it were truly unique, then it couldn't possibly be different. This would explain why we have this theory of everything and not some other, and would thereby fully realize the dream of a final theory.
This does not mean that the dreamed about unique theory of everything would be inevitable from a purely logical or mathematical standpoint, without ultimately making recourse to the physical world. Rather, the hope was that physicists would show that there is only one possible theory of everything that can describe an actual physical universe. While pure logic may allow for other mathematically consistent versions of a theory of everything, only one such theory would be capable of generating a real physical universe. Steven Weinberg elaborates on this point in his book Dreams of a Final Theory. He says as follows, I do not mean to suggest that the final theory will be deduced from pure mathematics. After all, why should we believe that either relativity or quantum mechanics is logically inevitable? It seems to me that our best hope is to identify the final theory as one that is so rigid that it cannot be warped into some slightly different theory without introducing logical absurdities like infinite energies.
Weinberg is referencing the fact that all known physical situations are of finite energy, and it seems clear that an infinite energy is physically nonsensical. In fact, the rejection of infinite physical energies as impossible is one of the primary methods that physicists have for discarding theories as nonsensical. Therefore, even if pure mathematics allowed for a different theory of everything, perhaps physics would not allow for it. For instance, maybe it could be shown that any variation on the theory of everything, or any alternative theory of everything, would result in a physical absurdity akin to an infinite energy. Such a discovery would render our theory of everything unique, insofar as it would be the only theory that can actually describe a physical universe. Achieving this ambitious goal would fully realize scientists' dream of a final theory and successfully explain why we have this theory of everything and not some other theory.
In case you're having a hard time following this point, let's give an analogy that can help clarify the difference between a unique solution and a solution that isn't unique. Let's imagine you see a house made out of Lego. You might wonder, why was the house built this way and not some other way? In fact, there are many different ways to build the house, and not just one unique way to build it. Therefore, it's reasonable to ask, why is it in fact this way? On the other hand, if you see a fully assembled jigsaw puzzle, you wouldn't wonder why the pieces were put together this way and not some other way. After all, there's only one unique way of arranging the pieces so that they all fit together. This analogy shows that when you have a unique solution for something, you no longer have the question of why is it this way as opposed to a different way. This is what scientists were trying to do for our laws of nature, to find a unique theory of everything which couldn't have been any different. It doesn't matter whether it was logically impossible, mathematically impossible, or physically impossible. The main point is that as long as physicists could show that it was some kind of impossible for the laws to be any different, they would be able to answer the question of why these laws.
Despite physicists' dream, it eventually became clear that there is no one unique theory of everything. Rather, they realized that there are many logical and physically possible laws that can describe a universe. For example, why couldn't our universe work exclusively by Newtonian physics? As scientists used to believe, there's nothing logically wrong with it, it just doesn't match our observations of this universe. From the infinite set of all imaginable laws, there is no reason to believe that quantum mechanics and general relativity are the only possible laws that could have governed our universe. As Paul Davies said, there is not a shred of evidence that the universe is logically necessary. Indeed, as a theoretical physicist, I find it rather easy to imagine alternative universes that are logically consistent and therefore equal contenders for reality.
Of course, not every imaginable set of laws is possible. The set of equations that governs our universe must be mathematically consistent. That is, they cannot contradict each other. Nevertheless, mathematical consistency alone is not sufficient to reduce the number of possible laws to being finite, let alone to one set of laws like quantum mechanics and general relativity. Lee Smolin, in his book, 3 Roads to Quantum Gravity, describes this realization. Looking back, it is clear that the assumption that a unified theory would be unique was no more than that, an assumption. There is no mathematical or philosophical principle which guarantees there to be only one mathematically consistent theory of nature. In fact, we now know that there can be no such theory.
The failure to find a unique final theory brings back the powerful question, why these laws and not some other set of laws? If many different sets of laws are both logically and physically possible, how can we explain why our universe has the particular laws we observe?
If we take a step back, we can realize that there's another way to explain why these laws, without finding a unique final theory. We can see if the approach that worked to solve the mystery of the constants will work here. We can examine what would happen to the universe if these laws were qualitatively different than they actually are, or if they didn't exist at all. When we do this, we can see that without these laws of nature, our universe would have no order, complexity, or structure. Aaron will provide a few examples, but I want to emphasize at the outset that while some of the examples may be a bit complicated for some listeners, try to follow the main idea.
Okay. The first example is from the law of electromagnetism, which says that opposite charges attract and like charges repel. This law enables the existence of atoms, combinations of positively charged protons and negatively charged electrons, which are held together by the electromagnetic force. If this law didn't exist, or even if it was reversed, so that like charges would attract and opposite charges would repel, then there would be no atoms or molecules.
That was kind of simple, Aaron. So you're basically saying that without the qualitative law of electromagnetism, there would be no atoms or molecules. Let's move on to the second example.
The second example is from general relativity, or the law of gravity, which says that all masses are mutually attractive. If the universe had no gravity at all, then there would be no galaxies, stars, or planets. This is because all these entities are dependent on gravitational clumping to pull and hold them together. Even if the law of gravity was merely changed from being an attractive force to a repulsive force, then all masses would fly apart from each other, resulting in too few interactions to produce anything at all.
Wow, Aaron, that was pretty simple. So you're saying that without the qualitative law of gravity, there wouldn't be galaxies, stars, or planets. Let's see the third example.
Our last example is from quantum mechanics. For centuries, scientists had thought that the matter of our universe is completely determined by the laws of Newtonian physics. But based on the new discoveries in the early 20th century, Niels Bohr, one of the fathers of quantum mechanics, put forth what became known as the Bohr model of an atom. Electrons orbiting a proton, like planets orbiting the sun. It was realized that this model is completely impossible according to Newtonian physics. For if Newtonian physics were true, then the orbiting electron would lose energy and spiral into the nucleus, thereby collapsing the atom. This is because an electron moving in a circle is actually accelerating, and the accelerating charge radiates and loses energy. This presented a serious problem. It seemed that the existence of stable atoms was impossible. This problem was one of the main motivations for physicists abandoning Newtonian physics and accepting the new qualitative laws of nature, quantum mechanics, with the quantum uncertainty principle, which allows for the existence of stable atoms.
Wow, Aaron, I thought you were getting the hang of this, but that was really complicated. Aaron is basically saying that if our universe wasn't governed by quantum mechanics, then there would be no stable atoms. These three examples show that significant changes in our qualitative laws would undermine all order, structure, and complexity in the universe. Without electromagnetism, gravity, and quantum mechanics, we wouldn't have galaxies, stars, planets, atoms, or life. Notice that none of these examples have anything to do with the quantities of the laws, but only with their qualitative nature. For example, we didn't discuss how strongly gravity attracts, but only the fact that it attracts and doesn't repel.
Furthermore, it would seem that entirely different qualitative laws would also fail to produce order, structure, and complexity. Imagine a universe whose only law was that every particle continuously moved in the shape of a triangle or square. Although you may need some imagination, the possibilities for alternative, logically consistent universes are endless. Would these universes result in any complexity at all? All evidence indicates that the laws of our universe are very special in their ability to generate a universe with any complexity and structure. In support of this point, Paul Davies says, "You might be tempted to suppose that any old ragbag of laws would produce a complex universe of some sort, with attendant inhabitants convinced of their own specialness. Not so. It turns out that randomly selected laws lead almost inevitably either to unrelieved chaos or boring and uneventful simplicity. In some sense, we live in the most interesting possible universe."
All this leads to a clear answer to the question of why these laws as opposed to other laws. That question is based upon looking at the form of the laws themselves and realizing that there was no indication that they're unique. However, we now see that what's special about these laws is not their form, but what they produce, a complex and ordered universe. In other words, the reason why we have these particular laws and not some other laws is based upon a teleological explanation. They were designed for the purpose of producing a complex, ordered, and structured universe like our own.
Based upon our appreciation of the design and purpose manifest in the qualitative laws of nature, we're in a position to formulate the design argument and demonstrate how it points to an intelligent designer of our universe. Our argument relies on two intuitive principles, which we just explained and supported with quotes from physicists. Let's review the two principles. Here's the first principle. The qualitative laws of nature did not intrinsically have to be quantum mechanics and general relativity. Instead, they could have been any set of laws that are mathematically consistent. And here's the second principle. For all possible sets of laws of nature that our universe could theoretically have had, the overwhelming majority of them would lead to a universe with no order, structure, or complexity.
Assuming these two principles, the design argument begins with physicists' question. What caused our universe to have these particular laws rather than some other possible set of laws? When we examine our laws, we realize that they aren't just any arbitrary set of laws. Rather, they are special insofar as they have the potential to unfold and generate an interesting universe filled with order, structure, and complexity. On the other hand, other possible laws would result in a universe lacking galaxies, stars, planets, life, molecules, and atoms.
This implies that the laws of nature were selected for the purpose of bringing about a universe like our own. And since the very definition of intelligence is the ability to choose one meaningful possibility from the set of all possibilities, this indicates that the laws have an intelligent cause. In other words, the design of the qualitative laws of physics shows that our universe has an intelligent designer, which picked out quantum mechanics and general relativity from the set of all possible laws for the purpose of creating a universe containing galaxies, stars, planets, atoms, molecules, and life.
We want to emphasize that we are not saying that the qualitative laws of nature were designed primarily for life or human existence, to the exclusion of all other aspects of our universe. This is because the many complex structures that are dependent on our design laws of nature include much more than life alone. Rather, the conclusion of our argument is that the qualitative laws of nature were chosen to bring about our entire universe in all its grandeur.
We would be remiss if we didn't mention how scientists respond to their inability to find a unique final theory. Because of the failure of science to show that our laws are the only possible laws of nature, multiverse proponent Max Tegmark argues that there actually exists infinitely many universes, each governed by a different possible set of laws of nature. He really believes that every conceivable, mathematically consistent equation describes another universe in his multiverse. In other words, because scientists can't explain why only our laws exist, Tegmark posits that all other possible laws actually exist.
Here's Tegmark. All my colleagues here at MIT that work in theoretical physics, they would love to come up with some equations which describe everything about the universe so succinctly that they can put it on a t-shirt, and students can walk around with them. And suppose you succeed and you make that t-shirt, and that describes all there is. Then you have to ask yourself, why those equations? Why not some others? Mathematicians study all kinds of different equations, and they would argue about which are more elegant and which are less elegant. But I feel that it would seem nuts if there was some basic asymmetry built into math, that some equations are allowed to describe a physical universe, and others aren't. So my guess is, rather, that every mathematical structure with mathematicians can study is on the same footing and describes a real physical universe.
We'll discuss Tegmark's theory in more detail in our mini-series about the multiverse. We'll argue why we think this claim is totally unfounded and describe what we consider to be its logical flaws.
Let's now compare the fine-tuning argument with the design argument. In the first 5 episodes, we argued that the fine-tuning of the quantitative values of the constants reveals an intelligent fine-tuner. In this episode, we're arguing that the design of the qualitative features of the laws of nature reveal an intelligent designer. While each of these arguments independently point to an intelligent cause for our universe, we would like to compare and contrast them.
Both arguments have the same basic outline. Our special universe only exists as a result of specific features of the fundamental laws of nature. When focusing on the quantitative features, the numerical values of the constants, we were discussing the fine-tuning of the laws. When focusing on the qualitative features, the nature of the laws themselves, we are discussing the design of the laws.
In either case, the question was, what caused the laws to exist in a way that results in a universe like our own, and not a universe that is nothing more than the sum of its individual parts? In both cases, we argued the answer to this question is an intelligent cause. Since both of these arguments rely upon the 2 principles we discussed before, for the sake of complete transparency and honesty, let's contrast how well the fine-tuning and design arguments justify each of these 2 principles. This will illustrate the strengths of the fine-tuning argument as compared to the design argument.
The first principle was that the constants, in the case of fine-tuning, or the laws, in the case of design, could theoretically have been different. When it comes to the constants of nature, a group of 25 numbers, like 137.035,999,139, this principle is very convincing. As we argued earlier, it seems clear that the numerical value for each constant could have been different and that a wide range of numbers are theoretically possible. After all, it seems unreasonable to find an intrinsic reason that the only possible value of a constant is 137.035,999,139 and not some other number. In fact, this principle was the basis for Richard Feynman's great mystery of the constants.
On the other hand, it seems more plausible to posit that the qualitative laws of nature are uncaused, fundamental, brute facts of reality. After all, the known laws of nature, quantum mechanics and general relativity, are fairly simple and beautiful, unlike the 25 or so constants of nature. Therefore, it's not entirely unreasonable to suggest that the laws are the way they are because that's just the way they are.
Nevertheless, since physicists can imagine other possible laws, they do in fact seek a better explanation for why we have these particular laws. After all, this is why they sought out a unique theory of everything, a pursuit which implicitly endorses our first principle that the laws could have been different. So while our first principle is not as compelling with regard to the laws as it is by the values of the constants, there is still a strong scientific motivation to try to explain the qualitative laws as well, and not just posit them as brute facts of reality.
Let's recall the second principle, that in the overwhelming majority of cases, different constants or laws would lead to a universe without order, structure, and complexity. Regarding the constants, scientists have rigorously assessed the consequences of them having different values. As we discussed previously, the discovery of fine-tuning revealed that changes in these numbers that would put them outside of a narrow range would result in a universe without galaxies, stars, planets, atoms, molecules, and life. Scientists can positively say, for example, that if the value of a certain constant was larger than X, then there would be no atoms. If it was smaller than Y, then there would be no stars.
On the other hand, regarding the qualitative aspects of the laws of nature, our second principle is not as obvious. To be convinced of the second principle, we must carefully consider the various alternative possibilities for the qualitative features of the laws of physics and assess the type of universes that would emerge. Would these new laws result in the structure, order, and complexity that our universe has, or are our laws supremely special in this regard? This is intuitively easy to assess, but hard to make rigorous. On the one hand, we can appreciate how the complexity in our universe emerges from the specific features of our amazing laws. As Davy said, it's hard to believe that things would work out so well with any ragbag set of laws. On the other hand, what exactly are the alternative sets of laws to be considered? While scientists model other possible laws for our universe and see that they lead to universes without any complexity, the theoretical possibilities are indefinite and endless, and therein lies the problem. How can we know that the overwhelming majority of possible laws lead to universes without order, structure, and complexity? Again, scientists intuit that our laws are special in this regard, but it remains an intuition of expert scientists, which cannot be rigorously demonstrated.
Because of these issues, we think that the argument from fine-tuning of the constants is stronger than the arguments from the design of the laws. Nevertheless, we have argued throughout this episode that these two principles are accurate with regards to the qualitative aspects of the laws as well, and that the design argument is also a very compelling argument for an intelligent design of our universe.
Additionally, once you accept the fine-tuning argument for an intelligent cause, it becomes much more reasonable and compelling to accept the idea that the qualitative laws of nature were also designed by the same intelligent agent that fixed the quantitative aspects of those laws.
We've now completed two independent arguments for an intelligent cause of our universe, one from fine-tuning of the constants of nature, and the other from the design of the qualitative laws of nature.
Next time, we're going to discuss the concept of entropy. This will lead to our third and final argument for an intelligent cause that emerges from a study of the remarkable order found in the initial conditions of the universe. So stay tuned. I'm Rabbi Aaron Zimmer.
And I'm Rabbi Dr. Eli Fader, and this is Physics to God.